Can start now. I think we can do it now. So, ladies and gentlemen, it's with great pleasure to welcome our distinguished panelists and participants in this important technical seminar devoted to innovation in filtration technology using ceramic flat sheet membrane solution versus conventional filtrations. My name is Hassan Abu Naga. I am Vice Chair of the Middle East Water Forum. And today we have more than 100 participants registered for this webinar from countries around the world. And for that, I would like to thank you all for your participation. For your information, we are also recording the seminar and we will share it with you after the webinar. And we would like also to ask our participants to type their questions in the chat thread to use the Q&A. And we will have also this Q&A at the end, so you can ask our panel any questions you would like to ask in their presentations. So in the beginning, to give you a brief about the Middle East Water Forum. The forum is a unique and pioneer platform for all water stakeholders in the Middle East. And the idea of the forum is mainly to connect various interested parties from industries, private sector, international and regional organizations, and academia together in order to exchange and gain knowledge and advance knowledge and actions toward achieving water security for all. And today we also sharing the state of the art of the technologies in all water and sanitation fields. And such innovative technologies are really significant in the Middle East. As you know, the Middle East is the most water scarce region in the world, with many challenges to achieve the Sustainable Development Goal number 6, which mainly goes to safely manage the water and sanitation. Consequently, waterborne diseases continue to spread and health risks also continue to increase, especially we are in today's in the time of COVID era. Membrane technologies have been widely applied, but many difficulties to large-scale application of membranes, including membrane fouling, energy consumption, and high investments, and all of this related to with the challenges in the Middle East. Among the various membrane technologies, today our panel will present Cerafletic innovation technology for ceramic flat sheet membrane with experience more than 25 years. And I would like first to welcome and thank our distinguished panelists for being with us today. And I would like to start introducing our panelist, Dr. Martin Kashik. He is a co-inventor of ceramic flat sheet membrane and the CEO with 30 years of experience in water and sewage treatment systems, applying membranes and physical chemical treatment technologies. And we have Mr. Kay Gonta. He is the chairman of the board of Cerafletic, co-inventor of ceramic flat sheet membrane modules and processes. We have also Mr. Julius. He is a chief commercial officer and a strategy and finance expert in charge of business development and expansion of the company. We have also Mohammed Sharaman. He is the director of Cerafletic MENA. He is expert in water treatment technologies for 2 decades. He also has been active in our region in the Middle East. Last but not least, we have Rami Ershidat. He is the executive director of Ershidat Water Treatment Company, and he will provide the successful technologies that has been applied in Jordan, which he is pioneering the use of innovative technologies in Jordan, including the use of the ceramic flat sheet membranes. So our agenda today will start mainly, if you can, Julius, show off the agenda. So we will start by technology introduction about what is going on about this technology. And then we will, Dr. Martin will provide some basics about this ceramic flat sheet membrane. And then we will discuss the products, process, applications, and presentation also about the technical details and the processes when it comes to this innovative technology. And we will have economic perspectives on that, since it's really very significant when it comes to the application in the Middle East. And then we will show will be a success story from the Middle East of using this innovative technology. And then we will see what is the experiences of that. And then we will, you will be having the chance to ask questions for our panelists. So without further ado, I leave the floor to Julius to start moderating the discussion and the table. Thank you.
Thank you, Mr. Hassan, for the introduction and also for the platform to speak here today, and hi to everybody who joined. Maybe a quick also from our side, feel free to throw questions into the chat. We've seen some already. We will try to cover them as we hit the different topics in our presentation, and then what's not covered, we will try to address those towards the end. To get us started on the highest level, and this is just a couple of slides, and then we'll pass it on to Dr. Martin, who will take a deep dive into the technology itself. But we want to take a pause here and take a macroeconomic lens on a similar industry, and you will see later why this is relevant. But we wanted to show the development of the solar photovoltaic industry here, and the dots will connect later. The orange line is outlining the solar panels cost per watt as it has evolved over the last few decades. And then the blue line is the install base of solar capacity. And you see there that right around 2007, 8, 9, 10 was a key inflection point for the industry that scaled the solar industry massively. So there were essentially 3 decades long of development, improving the unit economics of the technology through different means that decreased effectively the cost to a point of inflection where unit economics further increased scale and production picked up, and now solar has become from a niche market to a mainstream energy source with global wide acceptance and become a standard essentially for power production. And later you see all the dots connect, but just keep this in mind, because ceramic flat sheet membrane actually is going a very similar trend, and keeping the macroeconomic lens on it helps us project what the future will yield in water as well as in electricity. And this goes right to the next topic. GWI already wrote in 2017 that ceramic membranes are really at a tipping point here, with decreasing costs and specifically unit economics because of increase of performance and decrease in production costs, achieving commercial breakthroughs and further application advantages such as in seawater, oil, gas market, etc., is really leading to breakthroughs. And this technology is developing fast, and we are here today to share with you where we have been from the technology perspective, where we are today, and what is yet to come. The leading experts of the ceramic industry, they knew that ceramic is the next generation water treatment solution. The only challenge has been cost. And this is exactly what has changed over the last few years, similar to the solar industry, having hit a point where the unit economics are now where they are highly, highly competitive. We have details to this later. And then reaching this, this mainstream usability. And we will dive into details, but first, I'll pass it on to Dr. Martin, who will walk you through the one-on-one of the technology and guide us through the next levels. Dr. Martin, I'll pass on the control to you.
Okay, thank you. Welcome from Serapultec in Germany. So, okay, so the first slide shows where is, oh, sorry, Okay, so the first slide shows where the ceramic flat sheet membrane, where's the position in the wide field of filtration technologies. So starting with the very old and but still running technology, sand filtration, multimedia filtration. So with this technology, we have a pore size from around 100 micrometer, but this is not the pore, it's the particle size which can be rejected by a sand filter. So, and it's in the range between 100 micrometer and let's say the minimum is 20 micrometer. And then when we follow on this line, the next is the cartridge filter, and in the range between 10 micrometer and 1 micrometer, and then coming some polymeric membrane. And our ceramic flat sheet membrane is exact in the middle between the microfiltration and an ultrafiltration, so on the border between these two technologies in a range of 0.1 micron. It is also possible to produce this flat sheet membrane with smaller pores. Also, it is possible to go to 0.05 micrometer, but the most common is in the range of 0.1, 0.2. So means the wide range is between the 0.05 up to 0.5 micron. So in this range, we are working. So, and when we are looking, what can we reject? So it means we reject all the germs and bacteria. We also reject the TEP, which is often a problem in seawater desalination. So this technology is nice to treat seawater and reject this TEP. We can reject all particular metals, so especially iron and manganese. When we oxidize it to a manganese or ferric oxide or an hydroxide, so then it becomes a solid, and the solid can be rejected. And also the most of the colloidal particles which are in the water, mainly from bacteria, but also some inorganic compounds, can be rejected by our membrane. Which is not possible is to remove dissolved organic or inorganic compounds. So this means if you have an iron and if it is not oxidized, it is an atom, and this atom is so small and will passes the membrane. And also, of course, is all the salt, for example, the seawater salt will pass our membrane because it is not possible to reject it with a micro or ultrafiltration. So when we walk more in this direction, we have the ultrafiltration, which is typically polymeric membrane. And then after we can see nanofiltration and reverse osmosis. Both are also the polymeric membrane, which can then reject salt and dissolved inorganic and organic compounds. But the reverse osmosis, the flow direction is in the length of the module, and the spacer here inside is very small to maximize the membrane area in one module. So you have to protect this reverse osmosis module from clogging between the spiral wounds, membrane flats, and so our technology, the ceramic flat sheet membrane, typical is used as a pre-filter in front of a reverse osmosis or nanofiltration when you want to produce drinking water from brackish water or from seawater. In the case we have surface water with a high quality, and we only want to guarantee that all the turbidity is removed and the microorganism, then we can even produce drinking water from this technology. So the next slide shows how our module or how we can come from the membrane plate to a filtration unit, filtration plant. So the smallest piece is one flat sheet from ceramic, and we have put two end caps on both sides. So the flat sheet membrane, we have hollow channels in this flat ceramic piece, and the whole unit is inside of the water. The water runs from one side to the other. I will show it later how it works. So, and with 34 of these pieces, you can do a technical unit. So, and this is the smallest unit we are selling. It's one filtration module. The total filtration area is 6 square meters. Which is the outer area of the total 34 ceramic plates. And then you can build up a tower which goes from one module up to 15 modules. You can build up a single tower. So on the bottom we have 4 feet for the stand, and on the top there are 2 header devices, and from the connection there you can go to a collecting pipe. And we have some sprinkler pipes, so the whole tower you can lift on this 4 ends to put it in a tank. This single filtration tower also can be combined in a row or in a line with 2, 3, 4, whatever towers, and all are then connected with one header pipe where the filtered water comes out. And so, and these devices were put into a tank, like you can see it here. So this tank can be built up from concrete, from steel, from polypropylene, whatever best is for the site. And as we can see here, we have 3 rows of 3 towers, so in total 9 towers here, and all are connected here on the outside together. And then we have one suction pump and the produced water coming out at the outlet of the suction pump.
Martin, just to jump in here with one question that we saw pop up earlier in terms of capacity and footprint. Here we have a tank of about 3 by 3 meters producing in groundwater about 10 million liters per day, just to give everyone a little bit of a feel of how compact the technology can be. And then, Martin, on a second note, as we are going through it, I think we must pick up the pace a little bit to cover the remaining as well.
Yeah, okay. Okay, so as I said before, this is a submerged system. Filtration direction is from out to in. So, which means the plates are in the dirt water, the dirt bacteria, whatever, are on the outside. And during filtration, which is a suction, so we are sucking from the nozzles the water out, and the dirt builds up a layer on the surface of the membrane. So you can see here the membrane is built up in two. It's asymmetric, so means we have one substrate, which is a strong piece of the plate, and then a very thin, around about 50 micrometer, very thin filter active layer, which is also from ceramic. And on this layer, all the deposit will be collected and forms another layer, which forms this cake on the membrane surface. So, and the next slide is now when the cake is formed on the membrane, we have to, or it is necessary to remove it. This we doing with a backwash. Then the direction is reversed, so we go from in to out. And typical, we are using round about, let's say, much less than 1% for backwash. But it depends on the applications. There are also applications where we have to do much more often backwash, and then the amount can go up to, let's say, 10%. The backwash can be also enhanced by air scouring, which creates forces which are coming from bottom to the top. So, and how we do it in technical. So you see here this 34 plates on the top, this brownish, and they are all collected on the channel on the back side. And this channel is connected to big channel, which are on the side. So in total, we have 4 channels. And on this channel, on the top, there is this suction pressure. So the water flow is through the membrane to this channel, through this connection, and then the big channels up. And during backwash, it is reverse, and the water goes back, and so we can backwash each plate. And so this is the tank. So it's the same as we can see for one module. So then during filtration, we are sucking from all the three towers the same amount going out. And during a backwash, we press the water from the backside, and at the same time on the top there is an aeration, and all the deposit which comes comes down from the plate will be distributed in this tank. And finally we drain this, and this is the sludge which goes out, and then fill up again and doing the filtration from the beginning. So this technology was developed by Professor Horst Schmiel, who was a professor where I did my PhD, and it was the patent was in 1993. So the first drawing were made by myself. So the drawing you can see here on the right side was done by myself, and yeah, and we tested this on the university in Saarbrücken. The first small pieces, which were not bigger than 5 by 5 centimeter, and which was very new and very expensive during this time, similar as we saw at the beginning with the solar power. And so nowadays nowadays there are many producer, let's say worldwide at the moment, 20 producer which we are knowing, and the dimension means the thickness and the length and the width of the membrane is different, but in principle it looks very similar. In the beginning, there was only aluminium oxide as a membrane, but now also we have silicon carbide, and often also zirconia is used, especially for the layer on the top. And why we are using different materials, so it's a question of the price, but also the hydrophilicity of the material makes the difference. So especially when you compare silicon carbide with aluminium oxide, you can see the hydrophilicity is very higher for the silicon carbide as for aluminium, and of course much more higher than for any other polymeric materials like polyethersulfone or polyamide or PVDF. So, but not only the hydrophilicity, but also the zeta potential is very important. So when the hydrophilicity gives you an idea how much can be the flux through this material, the zeta potential gives an impression how good can a membrane handle materials which brings or which causes in a fouling of a membrane. And because in nature, the main organic materials, they have a negative zeta potential. They like positive loaded surfaces. So means the best is to have a high negative loaded surface to protect your system from fouling. And we can see here on the blue line, the silicon carbide has it over the wide range of the pH from 3 and up to the end. It's a very high negative potential and very similar to silicon oxide. The alumina has his neutral point at around 7. So because it's mainly the natural water is higher at 8, then you can also have a negative potential, but it's not as big as for silicon carbide. And when we compare our silicon flat sheet membrane or in common the ceramic flat sheet membrane with sand filter, so we can see that we are robust like a sand filter, but the pore size is much smaller. And on the other hand, the polymeric membrane has a shorter lifetime. It's more sensitive. The fouling is higher. So the frequency of replacement, frequency of cleaning is higher. So in total, it leads to a long lifetime, 2 to 3 times more, like in comparison with polymeric. And the water quality from the inflow, so we can accept more worse things like algae, high concentration of algae and all the things. So this is the big advantage of a ceramic flat sheet membrane. So I'm with the overview at the end, and so I want to give over to Kai, which explains more on the products. Thanks.
Thank you, Martin, and hello to everyone here right now from Serafiltic in Middle East, in Dubai. Before I start with the product, some questions. Or are there some questions? We have seen there have been some raised hands in the chat. If someone has right now questions to the slides from Dr. Martin.
The easiest is if you just want to keep going, I think in the interest of time, and then in the chat, you can read in parallel, or I'll bring up a few topics as we go. For example, one of them, I know you're speaking about the module housing now. There's a question about different materials and ensuring that different, let's say, temperatures and materials expanding at different rates, that this is being addressed, and I'll throw in the questions as you go.
Okay. Oh yeah, throw in. Yeah. Okay, good. So products. When we talk about product, we are talking about the single ceramic plates, including, call it a housing. This is in total a module. And this is the smallest unit as a product. So like other well-known technology developments, it basically started like the development like in a garage with that time a limited budget. First equipment came from, a hardware store, but sorry, someone is changing here my slides. Julius? Yeah. But it's more than 15 years back, really the first prototypes of module and how the things have started. So, but already 2 years later, the first commercially available module series was in the market. And the main characteristic of this product series is that we have exchangeable single plates and a kind of steel frame, steel housing around. And this is a very successful solution. You can see here, this was the first original one or the first developed version. Later on in 2009 and 10, here a larger version came into the market, and even till today, this kind of series or module version is used successfully for sewage treatment, sludge thickening processes, and yeah, a very first nice solution. Second, Commercially available series was then developed in 2009. The difference here is that we have a potted monoblock. That means each plates are together in one block. You cannot anymore change, but the advantage was that the whole thing became more compact. You still need a surrounding frame to put each module together into a connectable complete unit. And you can see here, this is an original one. And what you see down in blue is a version which came into the market in 2015. The third generation, 2017, is the first version which you can really operate with the maximum flux rate. So you can really reach out the maximum performance of each ceramic membrane, regardless what kind of, if it is alumina based or if it is silicon carbide based. It is actually a combination of series 1 and 2. Very compact with internal piping, but on the other side, you are still able to change each single plate. The whole surrounding housing is made of an injection molded fiberglass reinforced resin. It means it's fully free of any metal parts, and hence you can use it under harsh conditions in seawater or any kind of salty water. And this injection molded plastic or resin can be used for temperatures up to the boiling temperature. That means 100 degrees C. And therewith you can use really this product for any kind of applications, cold water as well as hot water. So you have seen different product solutions are in the market, successfully used, but in order to accelerate the global acceptance of the technology, there are plans, visions to bring it into a standard. A standard, as you know, I think from reverse osmosis technology, where you have a common vessel, and in this vessel, you can add any kind of elements in. The elements here, the RO elements, are similar to the single ceramic plates. And the vessel, with more functions the module has, with all these integrated pipings, is the module. So this is needed in order to accelerate the global acceptance. And if you have such standard, you can always decide for the best ceramic membrane suppliers, and each customer has different preferences. One needs to have maximum performance. The other is just looking for the price. Third one wants to have the best warranty, and the other is asking for fastest delivery. So if you have these standards, the customer can finally decide which kind of ceramic plate can be used. And for sure, it enhances also the entry for new ceramic producers or new versions. As long as it's always the same, you can implement it easy into existing projects or new projects which are already designed. So this is not only a vision, it already happened. The standard module size is in progress. What you can see here are some pictures from exhibitions last year and also this year. Already 7 ceramic plate producers using this new module standard, and these producers status of, let's say, Q2 this year have a production capacity of about 1 million square meter per year, which is about 80% of the total market, available market. Yeah, this was an overview about the product, the modules. Julius, do you see any questions? Then I will answer.
Yeah, just one question.
I will jump to processes.
Can you just address the expansion problem that we've seen in the past before the launch of the glass fiber reinforced module and different temperatures?
Yeah, actually, the main challenge is in the design. Let's take it here. The main challenge is if you have a ceramic system and you combine it with any kind of resin or plastic, is that one is extending with temperature increase or temperature change, and the ceramic more or less has no extension factor. So the challenge is always that you don't create any kind of tensions on the membrane, because the membrane is robust, but if you have a strong tension, there are risks to crack. So with this module right now and the position, how it is made and how the plates are in, you have how we call it a breathing module. That means the housing, the module can extend with temperature, but you don't have any force on the ceramic anymore. That's the reason, in combination with the selected fiberglass reinforced resin, is the reason why we can right now use the module in hot water applications. Before it was impossible.
Excellent. Okay.
Okay. Good. So then I would go right now to novel processes. First one is a filtration process, or related to the filtration itself. It's an active cake layer filtration. This is really unique. You can only do it with a ceramic flat sheet membrane. What you can see here on the left side is what Dr. Martin already have shown, is that you have the filter active layer from the membrane, and this is the inside of the membrane, the body, and you're filtering here from the outside to the inside. So when you filter from the outside, you still have here ambient pressure. Any kind of particles which will be selected here cannot get compressed. You don't see any force on these particles. That means you have here an uncompressed cake layer. We like to combine it with a snow field where nobody was working on it. You still have the small flocks, but it's not compressed in any way together. What happened is, if you can operate a system like this and you don't have a compression, you don't have here inside a pressure loss. So if you don't have a pressure loss, you can allow to let grow a cake layer on the membrane surface. If you combine it with standard pressurized system, regardless if this is a polymeric membrane or if this is a pressurized ceramic membrane, you have the pressure from the outside. That means you want to avoid any kind of suspended solids forming on the membrane surface, because you will have a compression. And with the compression, you create a very high pressure. So you're limited with pressurized system, you're limited to handle high suspended solid loads. Typically, you have a kind of pre-treatment before, maybe a sand filter or another separation before, but you cannot deal with high loads of suspended solids. This you can do with a ceramic flat membrane, and knowing it, and this is right now a novel process here, we have considered that this cake layer here, the particles which are collected on the membrane surface, have an additional function. And this additional function is an adsorption. So there can be used different adsorbents, manganese dioxide, HMO, or known as HMO, or powdered activated carbon. And with this one, you are able, with an ultrafiltration, which how Dr. Martin introduced in the beginning, actually just can remove particles. You are able, in combination with this adsorption process, to selectively remove ions or molecules, hardness precipitants, the soft organics, toxins, taste, odor, color. So it makes it too much more than only an ultrafiltration.
Then to jump in here, Kai, on another note, we also got this question here, like, now, can we remove PFAS? As long as you can either precipitate it or adsorb it, you can. So for example, combining ceramic flat sheet membranes with a layer of powdered activated carbon allows us to very effectively, about 3 to 4 times more effectively than GAC, to remove PFAS. The same with other dissolved contents, as Kai had highlighted. Microplastics, there was another question. We remove simply by mechanical removal. The challenge there is with microplastics that they can also be pretty sharp and hard, and that polymeric membranes are not ideal for it. Breaking the fiber with ceramic is very robust, so removing microplastic with ceramic is absolutely not a problem. TEP, also another question, removed, but through the negative charge and the low pressure operation of the ceramic flat sheet membrane, not so much by the active cake layer, but through different features of the technology itself. And then I'll go through it, Kai, as you continue to speak, and see if we can address some of the other questions at this point. But this is a very, very unique feature, as Kai mentioned, only possible with ceramic flat sheet membrane as a technology that allows us to achieve new standards and removal targets that with other technologies cannot be achieved.
Yeah. It's just short when TEP already was mentioned. The reason actually can be seen here is due to that we don't have a pressure on the outside, and TEP is known as a kind of jelly. It's a particle, but it's jelly, so you can squeeze it even if it is a bigger size, always through a very, very thin pore size. Even if you have a 0.02 micron pore size, you can squeeze due to the force the TEP through. When you don't have a pressure on the outside and the membrane is negatively charged, you're not able, it doesn't like to go to the membrane, and you don't have a force to bring this TEP through the membrane. Okay.
Before we jump, Kai, just two other points here. I know also in combination with powder activated carbon, we're achieving phenomenal dissolved organic removals. Von in the hundreds to below detectable, essentially just a matter of the adsorbent or how much adsorbent we are choosing in combination with the ceramic. But perhaps you can address TTHM and also fluorides.
The TTHMs, it's not related to, by cake layer filtration. First of all, with the cake layer filtration, what you mentioned with PFAS, you just imagine if here a particle or a molecule or an ion needs to go through, you have very small particles, you have a direct contact of the adsorbent, so anything what is going here through will be adsorbed. That's the high efficiency and the benefits in comparison to any kind of mixing process you have before, you have as another or common standard for adsorptions where you mix the adsorbent in the pre-treatment in. There, the adsorbent is not seeing the content, and they're not in contact then, and so you don't have an adsorption. The fluoride, I think Dr. Martin is maybe there a little bit more specialized. I think we can remove fluorides. We can also remove THMs, especially the THMs if you use here as an activated carbon, if you use activated carbon, powdered activated carbon as an active layer. But fluorides, Dr. Martin, if you can answer there.
Yeah, it's possible. Though the point is all the time how to transform it in a solid. So normally you do it with a pH shift, and then it precipitates, and that we can reject, and then if necessary go back to the original pH.
So this is the combined. Maybe we can then follow up with the person who asked, let's say in a separate conversation. We have there, it's also listed on our website, a process which is called softening filtration, where we are combining softening directly with ceramic filtration, as Dr. Martin said, classic softening, increasing the pH. Then we have the precipitants and defiltering then out the precipitants, and part of a co-precipitation of this softening process is then the fluoride precipitation. Okay, good. Next process, really a uniqueness when we focus on cake layer filtration or dead end filtration, and we have a high suspended solid load between the plates. You also need some functions to secure, to ensure that all these contents are removed during the backwash. So what is here unique in this process, you don't have this in the way, is a kind of shower from the top. We actually call it always here a dishwasher. First of all, when after a backwash is done and you have still loose sludge inside the tower, you need to flush the whole things out. You need to flush out the cake layer, you flush it from the top, it goes to the bottom, and you can drain it out. For this, we have so-called a sprinkler function. But we're also using the sprinkler with a little bit lower flow, and you see here highlighted in yellow, that means we are using chemicals to have here a very, very efficient, unique cleaning option. What we actually do is we spray the chemical, a concentrate of chemical, but a very low volume, on the membrane. It's like you clean your bath. When you clean your bath, you don't fill the whole bath full with water, as you know it from a CEB, a cleaning in place CIP solution. You spray just where you have the contamination, you spray your concentrated chemical directly on the surface. And you wait for a few minutes, and then you wipe it. Or here in our case, we just do another backwash, and the membrane is fully recovered. So this is really a unique cleaning strategy. And within minutes, you're able to fully reach the performance of the membrane. There's a question which chemicals are used. I will directly answer. It depends on the contamination. For any kind of organic or biofouling cases, we will use an oxidant, chlorine, for example. So we spray the chlorine on it. We are waiting a few minutes and doing the backwash. If we see it's scaling based, or it comes from even a coagulant, let's say iron based, we are using an acid. So we are lowering the pH and doing a redissolve. And then we're doing the backwash. Good. Okay, these are, let's say, really we have a lot of other combined processes, but these are really two of the key novel processes you only can do with the ceramic flat membrane technology. Right now to the applications. Before I focus on Middle East applications, I would like to give you an overview about a global overview about the technology. This technology is established worldwide. We have right now more than roughly 400 projects. We cannot really say the number because sometimes partners purchasing a stock and using it for 1, 2, or 10 projects. But about 400 projects we have already in 71 countries, known countries. And you see here in the middle, it's an application split. 62% is in sewage treatment and 38% is related to water treatment. Total capacity is almost 1.8 million cubic meter. This technology is established. We have the oldest plant, which we installed in 2005 and was running for 12 years. So even a proof that we have a very long-lasting technology here. But we also have a proof that this technology is suitable for large projects. The largest is in Saudi Arabia. It's Tabuk, which has been just installed and is in operation with a total capacity of 155,000 cubic meters. So if you see right now hotspots where this technology is really famous and is used, it all started in Europe 15 years back. But as you can see is that really hotspots are in Middle East and in Asia. Asia, interesting is that it's mainly used for sewage, especially for MBR. Alumina membrane are used there. And really leading for using this technology in any kind of water treatment applications is Middle East. I think the reason is clear, especially Middle East suffers from water shortage. Or let's say there is water available, but the water source is contaminated. So it needs a very good treatment solution, a robust solution. We have here very harsh conditions. So it's ideal a place to use the ceramic flat membrane. So Middle East is really leading using this technology. What are the key applications in Middle East? It's groundwater, seawater, surface water, and treated sewage effluent. For sure, the main source is seawater, which is used for drinking water, but the technology is highly established in groundwater. What are here in Middle East? The challenges for groundwater is it's a limited source, it's not renewable. Hence, you need here to implement a technology which needs to operate with very high recovery rates. And also, you need to have a solution which can operate with temperatures up to 65 degrees C. What are the removal targets? Mainly contaminated with iron, manganese, and radioactive isotopes. What's the challenge here for seawater? We have the Arabian Gulf and we have Red Sea. So it's, let's say, not really, both seas are not really open. There's a lot of population on the coast. So these kind of seas are, let's say, contaminated or have a higher level organic contaminations, as well as algae blooms affected. So this is really the challenge here. And the key process in seawater is desalination. So you need a very robust and reliable solution, pre-treatment solution, in order to protect the RO. For surface water, also surface water, Middle East is a limited source because you have here less rain and you have very high evaporation rates. So if you have water in a dam, it's a limited source. So when you want to use this water, you should implement technologies which have a very high recovery rate. Challenges here: turbidity, algae, bacteria, microorganism. And for, let's say over the last years, becoming more and more into focus to use is treated sewage effluent. Middle East has a lot of existing sewage treatment plants, but currently the water is not reused, just discharged, but it's actually already a ready source. If you combine it or compare it with using seawater or other water which also needs to be desalinated, you just need a further step to treat the existing treated sewage in order to reuse it. Here the challenge is, especially in the Middle East, also related to the religion, that you need to have a product which is 100% clean of any kind of germs and bacteria. So you need there really a solution which is reliable, robust, and can permanently, without any material decay, ensure a maximum removal of this kind of contaminations. What is the technology status? Groundwater, as mentioned, this technology is established. We have a lot of projects, have been done. And the plan is for government in Saudi Arabia that more than 100 projects will be executed where the ceramic flat membrane is specified. For seawaters, Mohammed will go then into more details, but successfully it has been demonstrated that the ceramic flat membrane is able to remove TEP in a maximum level, much better than polymeric membranes, much better than sand filters. And we also have shown, or the technology has shown, that it's economically competitive based on demonstrations. So next step is to demonstrate it, not only here in UAE, also in other countries. And the first reference will be in operation by next year. Surface water, it's similar to seawater. Demonstrations has to be done. We have a first reference in Saudi Arabia for a dam, and right now it's planned to demonstrate this technology in Nile water in Egypt, as well as in several dams in Jordan. Treated sewage effluent, first reference is running right now almost since 10 years. In Saudi Arabia, TSE is a big boom. A lot of references have been created with this technology over the last years, especially in Asia. Successful demonstration has been done also in UAE, and further demonstrations right now are needed in order to establish this technology also for this application. So right now, a short overview about, this is, let's say, the title of this presentation. What are the key advantages of this technology? Right now, from the technical point of view, we have 4 key advantages. The first is this technology can treat any challenging water. Any kind of suspended solid loads you have, any peaks in turbidity or algae bloom, this technology can do. And you don't need, therefore, an extended pre-treatment, and you are not limited, as you know it from other, where they're, for example, saying maximum turbidity should be 50 NTU. And above, you are out of any kind of performance guarantee. This solution can treat any kind of these challenging waters. Second advantage is, it can also remove dissolved compounds. With the cake layer filtration, you are able to combine it with an adsorption process. It means you can reach always the best water quality. You have new novel cleaning functions. Due to the robustness of the membrane, you can have this spray cleaning from the outside. You're able there within minutes permanently to recover the membrane. And the last one is you don't have a performance decay and you have a consistent water quality. And the reason is that you have ceramic. It is proven. We operated the longest plant more than 12 years. And from day one till the last day, the same water quality has been achieved. The material is insensitive. Okay, this is my part. Any questions we have? I didn't check right now, Julius, if you just can a little bit assist me, if there have been any questions before we go to the economic benchmark.
I think a lot of them have been addressed, and I think the remaining we will keep towards the end. So, for example, what is the maximum turbidity that can be treated is another one. I think you addressed it. I mean, maybe you can speak very high level to the maximum loads, Kai.
Yeah, maximum loads. Actually, the partners in the US using silicon carbide, they're operating in so-called sludge thickening processes. As the name already said, is the suspended solid load is extremely high. So you're operating there with 40,000 to 50,000 ppm of suspended solids. So it becomes already like a mousse au chocolat, the suspended solid loads, and you're directly operating there. So you don't have a separation or settling before. This concentration of suspended solids is in direct contact with the solution. So we can say for, let's say, drinking water applications, we have no limits. We can use any kind of, or it can operate in a direct filtration with any kind of suspended solid loads and turbidity level.
And the same, essentially, also we're seeing a comment here about algae. I mean, for sure, the algae, we have an application where it's essentially covering the membranes to a certain degree, right? So there's also with algae no limitation. We know this is a big topic in the Middle East here, as well as in TSE plants.
Yeah.
Okay. Good. Then let us dive into the economics a little bit. If you remember from the very beginning of the opening of the presentation, you see an inflection point as we're comparing at the macroeconomic level ceramic flat sheet membranes to the development of the solar industry. And the reason why we led with this is because we are seeing a very similar trend here with ceramic flat sheet membranes. If you look back from 2005, when the first plant was essentially installed with ceramic flat sheet membranes, the unit economics have improved by about 10x to where they are today. These improvements are driven by a number of factors: performance increases in the membranes, launch of new high flux modules that empower the membranes to operate at higher flux, and economics of scale kicking in as the adoption of this technology is reaching wider and wider extension. And we're now at a point where we see exponential growth of production capacities and demand of the technology in many, many more markets. And it is easy to project where this will go. It will become, and this is why we're here today to share with you, an absolute mainstream go-to technology in many applications, the standard. We dive into the economics in a second, and then you can see why we believe in the next 5 to 10 years, ceramic flat sheet membrane will be the dominant UF/MF filtration technology in the space. We know that sector itself, or the industry, water treatment, is moving relatively slow, but the technology has already achieved a point where it is commercially and qualitatively superior to the polymeric UF and MF membranes. And this will take a deep dive now into a little bit further. We have the next 4 slides go now on the capex of membrane equipment per cubic meter filtration capacity for 4 different applications. On the right side, the total cost of ownership, TCU, for these installations. So groundwater is certainly the application where ceramic flat sheet membranes are the most competitive. On the left side, you see compared the pressurized and the submerged polymeric membranes in the yellow and the orange bar. And then you see in the blue bars, in the dark and in the lighter one, the silicon carbide and the alumina membranes. And a few takeaways here is that first, in 2015 is when we had one of these big breakthroughs where you see the inflection points coming down. The ceramic flat sheet membrane still being more expensive, but the knowledge from 2015 is not what it has been, what is today. We're seeing high competitiveness on just the ceramic capex already, because of the higher flux rates that the ceramic is able to achieve. And we see this trend to continue to capitalize on further economies of scale, making the technology more and more competitive. One, let's say, asterisk we must explain here, the pressurized polymeric membranes, yes, they are cheaper on the capex basis per essentially for the membrane equipment itself. But what is not included here is the additional pre-treatment capex that one must expense. If a pressurized polymeric membrane must operate with, let's say, feed water with peak events or high turbidity, it requires certain pre-treatment that the ceramic flat sheet membrane is not needing. So from that perspective, it's not completely apples to apples, but we wanted to openly share how the capex looks like. And then on the right side of the screen, the total cost of ownership. And this is where we see the biggest advantages. And it's a key as more and more projects are moving towards a build, operate, transfer model, BOT module, where the initial capex is only one component. What matters really is what is the cost, the total cost of the plant over a period of time. And we see massive advantages with the ceramic flat sheet membranes, specifically in the replacement cost on the power consumption side. Able to yield significant advantages over pressurized specifically, but also submerged polymeric membranes. So in groundwater, we see a total cost of ownership advantage of 66% for groundwater. And if we switch over, let's say, to treated sewage effluent TSE benchmark, we see a total cost of ownership of about 25%. The ceramics certainly a little bit more expensive on the capex per cubic meter filtration capacity, but again, the power consumption and the replacement costs make up for the little bit larger upfront investments over a 15 period of time. Big advantages for the ceramic flat sheet membranes. Surface water. As a benchmark here. So this is lakes, ponds, rivers. We see the ceramic flat sheet membrane essentially going the same trend on the left side of the screen as in the previous applications, each time a little bit different, mainly driven by flux rates that we're able to achieve with ceramic flat sheet membranes. And on the right side, also a total cost of ownership advantage of 18%. Kai, pause me if you see questions come through that we might want to answer.
I'm checking, yeah.
Interject if.
Nothing so far. Go ahead.
And then on the last of the 4 applications, which is a very important one in the Middle East, seawater, we also have a significant savings in the total cost of ownership of roughly 24%. But what here is to be highlighted is that I think there are a lot of very important cost items that are not even part of this equation. For example, the cost of the plant not operating at the targeted capacity. When you have failures with polymeric membranes and you're not able to achieve for a period of time the design flow rate, this is a cost that is not quantified here. When you have to do frequent backwashes, frequent chemical cleanings, then valves are closing and opening frequently. And this cost is not considered that this equipment that is operating at harder conditions, valves, pumps, also need to be replaced more frequently. When you have ceramic flat sheet membranes, the plant can operate more smoothly, less opening of valves. The pumps are not as expensive, operating at lower pressure. This has indirect saving opportunities. And lastly, we know there's the saying, right, just in the restaurant industry where everything matters about location, location, location. In seawater, it's about pre-treatment, pre-treatment, pre-treatment. If you get the pre-treatment right, then the cost of the plant or operating the entire plant is smooth and headache-free. If you have a bad pre-treatment, it's 20, 30 years of headaches. And this is where the polymeric membranes have a big problem. When the RO is not working well because of the pre-treatment. And this is the problem that ceramic flat sheet membranes are solving. As Kai mentioned earlier, consistent water quality and no decay in performance, leading to very smooth operation of the RO, also due to the removal of TEP. And this is where the real dollars are. So this slide is great to see on the total cost of ownership savings for the membranes or for the pretreatment, but one must consider the entire plant where the biggest cost item is with the RO. And then to conclude the commercial advantages here, just as summarized as the technical advantages, less replacement cost is a very, very big one. A very long lifetime of the ceramic when operated correctly, outlasting 10 years easily with no performance decay. One of the biggest advantages that drive economics. Very low power consumption. Most of the applications we operate with negative 0.1 to negative 0.3 bar pressure, and correspondingly the power consumption is very low. Only enabled by the out-to-in filtration. Then simplified pretreatment, saving additional capex of the entire plant. At the end, what matters is the cost of the plant, not the cost of the membrane. And we can simplify the entire water treatment process chain by avoiding clarifiers, sand filters, or other pretreatment steps that make the system not only more compact from a footprint, but much more simplified from a treatment chain perspective, and therefore saving capex and opex. And then, as mentioned earlier, the extended lifetime of the surrounding equipment, and especially the reverse osmosis, achieving additional yields for the entire plant performance. So I pause here. This is the economic side of things. Perhaps if I miss questions during the Q&A chat here, we can address those towards the end. And I'm passing it on to Mohammed, who will take us through the success in the Middle East.
Thank you, Julius. Hello, everyone. To make it short, I think the time is ticking. That for the ceramic filtration Middle East, it's actually started in 2011, where Sky promoted the technology in Saudi Arabia at that time. And they started the first plant in TSE application, treated sewage effluent. Was the reason that the customer at that time, he wanted to discharge this effluent sewage to the seaport. So there's a regulation and limitation on the quality that should be discharged to the port that time. And this was 300 cubic meter per day. And till today, I think it's almost running well. And with this technology or this treated sewage effluent in general in Saudi Arabia and most other Arab countries, it's, we call it viable for option for resources, water resources in Arab countries. To save the current fresh water using the fresh water in such applications that can be used the TSE effluent with further treatment and reuse, especially with our ceramic filtration. And during this stage, there was a lot of demonstration and studies done by our team that time in Saudi Arabia. And they, after the success of demonstration and studies, they started with one plant in Saudi Arabia in Qasim. Julius, you carry. The demonstration was on using the hydrous manganese oxide with the ceramic filtration as a combination, as a cake layer on the membrane. You see in the slide, this is during the demonstration and the study. They spent, I think, a lot of time on this benchmark. And finally, in Directorate in Qasim and Ministry of Water, they decided to demonstrate the technology on real plant to replace existing polymeric membrane, which was in that plant, Boreda, Julius. One slide before. Yeah, one or more.
Sorry, it's switching a little bit late here. I'll keep it here now. 1 second.
Okay.
It's
with this
on the
study,
with
this study and benchmark that the ministry decided to specify this technology as the most reliable and high performance technology. That's why it's again become a standard for a groundwater treatment in Saudi Arabia. And next slide, you will see there's 120 projects already specified with ceramic flat sheet membrane technology for, let's say, all projects for all groundwater projects in Saudi Arabia for next, I think, 5 years from now, or 5 to 10 years from now. And in Boreda, and as I said before, that we install and we replace existing polymeric membrane that time. It was unable to handle this high oxidant water with high temperature that I think still it's working on to more than 50 degrees. That's why it's for very short time that this ZWID 1000 need to be replaced, and that time Kai and the team replace it with for larger plant in total capacity 100,000 cubic meter per day, and the target was in removal for iron and manganese and radioactive isotopes as a pre-treatment for the existing RO or nanofiltration system. Also, next plant for the same issues that also ministry, we replaced the existing MEMCOR, which is another brand of polymeric membrane for the same reason that it's not able to handle this high oxidant water and high temperature. And this technology became a standard, and we have now 3 providers for this technology, and all have this NSF certificate on hot water, which is now mandatory by ministry that any membrane for a groundwater should have this NSF 61D hot, which is certified for up to 60 Celsius degree for, most of the groundwater everywhere, it's like hot water. And existing technology and UF technology or others, it's limited up to 23, which is cold water. And only the ceramic can work in this hard conditions with high oxidants, high iron, manganese concentration, all others with high temperature. And after the success of these harsh conditions, we also started demonstration in 2018 for the seawater application. Also, the site was very challenging. Maybe we selected the worst seawater in the Gulf region. And that time, there's 2 other filtration processes are already there, and the comparison on real site with sand filter and polymeric filter and our ceramic filtration. What we see that the main reason for the biofouling in seawater is mostly the TEP and algae and suspended solid and high turbidity. And during our 8 months demonstration, we got a very, very promising results, which is the best filtration process to remove the TEB as well as all other impurities, like algae or suspended solid oil, which is available in the seawater with the high concentration, and all other particles. Also, we, after this in the Gulf region, Saudi Arabia and demonstration and many references in Gulf region, we started in Jordan. We started with this Mashta Al Faisal plant, their first project. The gentleman, our customer, is already here in panel list. He will give you more data about this project, but the project was replacement of existing sand filter, salt filtration unit. The water's most challenge that have high iron concentration in the raw water and highly hardness and all this. And he decided with the ministry that to change the existing process by the ceramic that time. And the beauty that time also that we did the shift between each, that because our system is compact and we immediately shifted from the existing to the new pre-treatment solution. So I remember that time we have only 48 hours to shift from the old system to the new system. And we got the massive support from the client and the ministry that time to do it. And we success, hopefully, and Mr. Rami can explain more about this site especially. Also in Jordan, we also started more and more distribution, this technology for many applications. And in Jordan, as well as Saudi Arabia, they have issue with isotopes, radioactive isotopes. And we installed 2 plants there for this targeting removal of this radium and in general, the radioactive isotopes. Also, we installed another plant in, for E. coli removal. And it was also very successful. Also, Mr. Rami, he did most in Jordan because he's become the pioneer in Jordan for this application. And now I will hand over to Rami to give more details about his experience in Jordan, how with our technology. And if there's any question, please add in a QA, and we'll have a chance to answer your question. Take the lead, Rami.
Thank you, Muhammad. My name is Rami Irshadat. I'm CEO of Irshadat Water Treatment in Jordan. In Jordan, what happened, to be honest with you, we took kind of a leap of faith. Muhammad was very convincing, if you will. At the beginning, it was 2016 when we started talking about the technology. It was in its modern form, if you will, as Seraphytic. It was brand new. I took the decision to actually place an order before I had an order. That was the leap of faith, and it paid off very well. In Mashta Al Faisal, we had a perfect situation, almost like a lab experiment, because we had all the readings of before and after, if you will. So what we had in Mashta Al Faisal as pre-treatment to our RO system was sand filtration and 2 stages of microfiltration, 5 microns and 1 micron. So it was extensive, and yet we're having so many problems with iron. Dissolved iron is really nasty. And we've been running the plant for 6-7 years at that point, and I was looking for a solution because iron was getting into the membranes no matter what we did. Oxidation, aeration, microfiltration, it did not stop it. Normal ultrafiltration or polymeric ultrafiltration was out of the question, because if you have high concentration of iron, that you'll get immediate fouling with these kinds of membranes. So ceramic was, and flat sheet bed ceramic was a godsend, if you will. It was, but the problem is that at that point, in that form, for me, it was not, hasn't been tested. And so we took the leap of faith and we got the approval from the Ministry of Water for an expansion and plant. And that's when we took the chance of upgrading the whole pre-treatment for Mashtal Faisal and upgrading, making the expansion of about 20% extra capacity. So what we did is we removed everything. And what we removed, the footprint of the sand filtration and microfiltration treatment was almost 10 times of the replacement of the picture you see now here, which is the Serafiltic installation. It took us at least 48 hours to switch over. It was exactly 48 hours. I mean, we worked day and night. Zero sleep, and I mean 48 hours of work. It wasn't easy. We were under extreme pressure because it was the middle of the summer, and we were under extreme pressure from the client, Ministry of Water, of they wanted water back, and we succeeded. And the great thing about our installation is that we can give you exactly what happened before and after. The advantages of the system, of the changeover from conventional to ceramic UF were incredible. We had, I'm sorry.
Rami, you can switch directly. I gave you control.
Yes, I'm trying.
Lagging a little bit.
Yeah.
Okay, then just tell me when to switch. I'll switch for you.
Okay, right there. Okay, right there. You can tell now this is from our old microfiltration bag filters. All the red color you see is basically oxidized iron, and the same on the membranes, as you can tell. At the end, we got huge advantages from the switchover. We removed iron was, we were testing 0.5, 0.6% ppm after pre-treatment, I mean, with the old system. And with the ceramic, we got 0.1, 0.2, and even less. Recovery of the pre-treatment and the old system was around 92. With the ceramic, we went over 98%, about 98.5%. So we saved a lot of water, and we need that in Jordan. That was a very, very important point. We got higher quality, we got more water, and then another big advantage is that we got to be more aggressive with our RO treatment, with the recovery of the actual RO treatment. So if you take all these points into consideration, honestly, the plant paid for itself, but of course over a big number of years. We got more water out of the RO system. We got more life out of the RO membranes. Of course, the experience, it had up and downs. We had the learning curve was fast, but we had to go through the curve itself. All problems were solved. Programming of the backwash rates, how, when, how strong, all that. It took us a few months, but eventually we got there. And we got great results from this plant, as I told you, and then we moved on. We actually were lucky that we were able to install 4 plants in Jordan with different applications. we were able to use the UF pre-treatment for removal of radioactive isotopes in 2 plants. And that's a problem we have in the south of Jordan. The aquifers in the south of Jordan do have radioactive isotopes, alpha, beta. And we got consistent results of 90% removal, and that is excellent. Anything over 80 is excellent. We also had a 4th plant that for microbiological removal, E. coli in particular, that was in the Zarqa area. We also got great results. So as you can tell, we have a wide spectrum of use of flatbed sheet ceramic UF membranes. And we have been able to be successful in all of them. To be honest, you need to have highly qualified technicians and engineers following these plants. But once everything is smooth and running, it's almost too easy, if you will. Everything becomes automatic, everything becomes repetitive. And that was basically our experience in Jordan from 2017, if you will, when we started work, and until today. And hopefully we're hoping to expand the use of flatbed ceramic UF membranes for all iron removal applications, for all high turbidity applications, and of course for RO pre-treatment. And that's basically our experience. If you have any questions, please let us know.
Thank you, Rami. Thank you.
And thank you for also pioneering. I know aside from ceramic flat sheet membranes, you're known to pioneer technology in Jordan. And I think we really appreciate, of course, as not just Serafiltic, but also as ceramic flat sheet membrane technology evangelists, for you to embrace this technology and show the rest of the market what is possible with this solution.
Mm-hmm. You're welcome.
Mr. Hassan, I think we are through the deck, and we can start with any type of Q&A. I think a few we addressed as we went, but perhaps you can give us guidance how we should proceed from here.
Yeah, thanks so much, Julius, and every speakers. You have provided really a good presentation, informative about the way we can go forward. Really, it's a promising technology that could be applied in the Middle East for 2 reasons. One reason is mainly about limited water supply, but also the type of water supply in the region is much different from another cities, since we have intermittent water supply in which people receive water only once or twice per week. And you know, there are much challenges towards that. I would ask the second remark or opportunity to use this technology is mainly that 80% of our wastewater is being discharged without treatment, and you know there are major consequences on that. I would like to ask specific questions to all the panelists, and we may also have another questions from the participants. You may, Julius, stop sharing the screen so we can, the participants see all of us. I think we have like about a little more than 20 minutes to reply to these questions. As you explained on, you know, in the technology itself and the process, there are major challenges in the Middle East when it comes to the operation itself, about how much, about the cost and the energy associated with the technology, but also with the personnel, as also Muhammad was explaining about having technical expertise or the people who are operating and maintaining this system, and also unreliability or uncertainty of different issues when it comes to water supply from climate change extremes like floods, when like an example in Jordan where water turbidity is very high in winter times, this stops the treatment, and so all of this has been influencing also the way we treat the water. So could you give me an examples of what are, or you tell us what are the guaranteed lifetimes that can be given within the context of Middle East of challenges, as I said, of unreliability and also maintenance and operational point of view? Thank you.
Julius, who's answering? Me? You?
Yeah,
Yes.
Kai, you go ahead.
Yeah.
Yeah, actually, for someone who's interested in selling even this technology, unfortunately, this technology lasts too long. So what we can say is that, to be honest, based on the experiences, is we have done these experiences in Europe as well as the Middle East, that the lifetime is which can be guaranteed more than 10 years. The first plant which has been installed was for sewage, was operating 12 years, and after 12 years there was the replacement. But the reason for the replacement was not that the membrane was damaged or not in function anymore. The reason was that the latest product version leads to savings in operations. So the customer decided, even having still a functional membrane, to switch to the latest version. It's like you have your Nokia mobile phone. It's still function, but you're using a new smartphone. You're buying this because you have a lot of benefits. So what we have seen in Middle East is more harsh conditions, higher temperature, more challenging water, drinking water. Let's consider the first plant we have installed in Saudi Arabia, in Buraydah, installed in 2011. Currently, there are discussions about the replacement. So we have here also 10 years operation. So what typically is given is a warranty of up to 10 years. From the material side, we hear from, let's say, ceramic will last more or less forever, as long as you're not using any strong tension, earthquake, or hammer. But the surrounding equipment, especially right now here with the new fiberglass reinforced, the producer, which is SABIC, gives the indication that this will last even under harsh conditions up to 20 years. So to summarize it, 10, 20 years, this is what we are typically providing information is the typical lifetime. We are even open, maybe Julius, you want to add something in, giving even guarantees up to 20 years, as long as you're operating the membrane as we are providing a guide. So then nothing actually can really happen with the equipment.
Yeah, maybe this is also good to interject here. For sure, let's say, we believe, and we are quite confident based on the information you have seen, perhaps you agree that ultimately ceramic will become the go-to technology for a wide variety of applications. Yet it is not yet fully understood by every single large OEM. So Serafiltic in particular takes a role in making sure that the OEMs and our customers fully understand not just how the technology works and how to install it, but also how to operate it. Because we know when it's operated well in the right way, then it lasts a very, very, very long time. So our role is to provide the right tools and mechanisms to ensure the operation is done the right way. As Rami mentioned, the right process is incorporated, the right backwash frequency, etc. And then it's like almost too easy to run fully automated.
Okay, and how is the operation of this technology could be different from other technologies, like many technologies of membrane, especially depending on also the type of the treatment, whether it's for drinking water or wastewater, or even for seawater. How this could be different of the technologies between us, and why we should emphasize on the role of ceramic of the ceramic filter membrane to be used in this regard. And how do you see the ceramic filter is much competitive depending on the use of it.
Regarding the operation and the differences, actually, the beauty of this technology is it forgives operating mistakes. Mistakes always happen, even if you guide probably, or let's say peak events coming where the operator is not prepared. You know, it happened. It's a reality and everybody's doing it. The question is, if then is your material damaged, or if it is, let's say, blocked in a way, is the operator able to recover the system? So the beauty of the ceramic membrane is it forgives mistakes. In worst case, we're always saying is you need to clean it.
Yeah. So maybe we also
sometimes that
the
means
same
you spend
questions
a little bit more in chemicals, and they have this beautiful function with the shower from the top, this cap clean. So even if something happened, within a very short time, you recover the system. And this is really a key point where the operator is always looking for, having something where you have a reliable operation.
Yeah, thank you. So maybe there is also in the Q&A also some questions regarding the operation. So maybe you can choose which questions you would like to answer so our panelists can take the
Yeah,
ones
I have
that
seen one question
interested.
here from Mr. Bassam is, what are the main challenges using ceramic filters? Actually, two main challenges. The first is during installation. When the material is on site and you're doing the unpacking, you're doing the assemble module by module, what can happen is that due to, let's say, wrong handling or strong vibration, or you use a tool, something cracks the membrane. This we have seen several times. That's it happened, especially when you install 1,000 or more modules, it will happen. Then you need to have a way where when one plate is cracked, you don't change the whole module, you change the single plate. So this is what we have here right now with the latest version. That's why we wanted to have exchangeable plates. So this is really a challenge, but happened during installation. Once installed, one time in, it is safe. So during operation, the main challenge is if, for example, let's say air scoring system is not properly in operation, or a drainage was not properly done, and you're increasing the sludge concentration very, very high, what can happen is that between the plates, you're forming a cake layer. You don't have a distance anymore between the plates. So here's a filter. So here, I mean this gap. And if this gap is completely full with sludge, what can happen is when you then do a backwash, you create a tension to the ceramic and it will simply crack. This also we have seen. So these are main challenges. Let's say strong tension, strong forces, as you have from your ceramic cup, maybe when you drink, you know, you let it fall, it will crack. So if you have any kind of strong mechanical force, it cracks. But chemically wise or temperature wise, you don't have any of these challenges.
Okay.
So, but Kai, to add to this point, that's why
I answered this proper.
Yeah, but just to elaborate, they also, you know, we're providing full guidance that mishandling doesn't happen, how to protect the ceramic during installation, and then most importantly, how to operate the ceramic given certain feed water quality, that this sludge buildup between membranes doesn't happen, that backwash, chemical cleaning, and entire process philosophy is designed in a way that the operator doesn't get into a situation of sludge buildup. But for operators that, let's say, don't have the knowledge and not seeking the knowledge, then these are the accidents that we have seen in the past.
Okay, I think also this also corresponds to Muhammad Heikel question. He said, as we know, ceramic expansion with temperature different than the header material, which cause broken the ceramic. How we can solve that?
Yep. I was a little bit answering it already, but let's say, or simply say, is the module design we have is in a way that the frame or the housing around can breathe. So it means any kind of temperature expansion, the plastic can do, but you don't create a force on the ceramic. I see that he's experienced from a previous version where you have a steel frame and there have been some springs. And the springs brought the tension on each module. So what happened is when the temperature increased, the module housing was then also trying to extend, But due to the spring, it was not possible. What finally happened is, we have seen it, when we took the material out, the ceramic was cracked. Yeah. Okay. So that was one of the developments of the latest module version, that we find a way, regardless the temperature and the changes, the temperature extensions of the module equipment around, that there is no force on the ceramic.
Okay. And is there any limitations on the feed water when it comes to its capacity? Yeah, and the type of pollutant and effluent, and also like different sets of different challenges, like it comes in the mid-time. Like sometime the turbidity is very high in the winter when there is a floods or something like this. So how the operator can manage to handle that?
Yeah, actually, when it is pure turbidity, regardless of how it is, you can filter. But typically, it's not, when the turbidity is high, it's not only turbidity, it will also contains, let's say, other contents. So the beauty of the ceramic flat membrane system is, as mentioned, it can handle any kind of suspended solid loads. We can add a coagulant in. We can even add, for peak events, a high dosage shortage, let's say for a week, when you have this kind of event, you add a high concentration of a coagulant in order to remove the dissolved contents and hence to operate during this peak events. The only change you then have probably is, if you have too much suspended solids, you have, instead of 2 times a backwash per day, you have maybe 3 times, 4 times, or 5 times. So what changes is your recovery rate, because you're creating a little bit more backwash waste. Other challenges, if you really ask challenges, what is, let's say, in good, what is a challenge for in the raw water? It can be, how is it called, detergents, surfactants. So depending on, you know, they are attaching on the membrane, let's say when we have laundry application. So it can immediately attach on the membrane. It's a question of, is it positively charged, negative, or anionic, cationic. So it can modify the surface of the membrane. And if we have from this too much, sometimes we are seeing it in sewage, in TSE, in treated sewage effluent, that we still have something like this in, or biopolymers which attaching the membrane. You have a very fast pressure decline or performance decline. What there helps is also, again, the cap clean. You spray from the outside, strong concentration, shortly, chlorine on the membrane, and you crack it. You crack the function of this surfactants, then you do a backwash and it's clean. But having this permanently in high concentration, I can tell you, this is an application where even we are saying, you know, it's very challenged to have a stable operation.
Yeah. Maybe we can take the last questions from Hanan Kuni. She was saying, how many years does it take to reach the break-even point after switching from the traditional treatment to ceramic? I think this debate.
I can answer this quickly. Yeah. Oh, Rami, you go.
No, I'm sorry. I'm just going to assume that this question applies to an RO plant, let's say, so we can, you know, have some kind of calculation of a difference between traditional and UF. I mean ceramic. In my experience, and it's more prevalent now, the extra costs of installing a flatbed ceramic pre-treatment compared to conventional. And please correct me on this, guys, 20% extra, 25 maximum. I mean, am I in the right range? And I think payback in a case like mine, where I get paid for every cubic meter produced, would be a year. But that's a special case because I have a BOT project where I get paid for each cubic meter that is produced from my plant. So it depends on what you're looking at. That's my experience.
Okay, we may take, Yolis, if you wouldn't mind, we can take 2 minutes reflections of For all the panelists, we have less than 10 minutes to end the webinar. So maybe we can start with Mohammed Sharman, and we can go back to until we go to Dr. Martin.
Okay, thank you, everybody. Wish we are able to support you all. And from my, okay, I'm part of Serafiltech, but this technology is promising for the people and for the humanity to use the water, especially in the Middle East, as the most scarcity area in the globe. And with this technology, I think we are able to achieve more and save our water in this globe.
Thank you. Right, no, thanks everybody for your interest. I hope we have been able to introduce this technology and have been able to also to show how successful this technology has been used and what is our vision in this region to successfully have in different applications this technology in operation.
Maybe Dr. Martin?
Yeah, I want to highlight in Germany, we are doing lab investigation for any problem with waters. And for this, we developed some lab equipment, but also a suitcase unit where we can go on site, which can be also ordered from us. For example, if there is any system integrator which want to work continuous with our technology, so then this suitcase unit is very, very helpful to get an impression, what is the quality I get from this membrane and how could be the flux rate and the procedures. You can see it on our website. This is a core to develop the right process for any application. Finally, I want to thank you for your attention and yes, bye.
Thank you, Dr. Martin. Yeah, I think it is key, especially as this technology continues to find wide-scale acceptance for people to experience firsthand themselves. And for this, it's terrific to have like a small unit you can use on your own plant or at other plants. From my side, I'm that convinced that ceramic flat sheet memory as a technology will become the de facto standard in all major key applications. It's just a matter of time. From the quality side, it makes sense, and commercially you've seen on the total cost of ownership, we're already there, and it continues to become more dominant or superior for the customer, and this is what matters. So it's great to see such a large number of people being excited about it. As Mohammed said, we are also quite passionate about actually solving water problems that impact the people, whether it's bacteria removal, reuse of water in Middle East, where the sources are very, very scarce and water really, really matters, as well as in the United States for removal of PFAS and other carcinogenic toxins in the Europe and Asia space. So we are super passionate about the problems we solve, and we believe the technology is providing us the tools to do so. And anybody on this panel or on this webinar who is interested to learn more or has a specific project, you can share with us more information, and we can, whether it's an academic exercise or real plant, we can share with you the benchmark, how ceramic would stack up to the, let's say, competing technologies or different solutions. We are happy to share our knowledge. We've posted a lot of information on the website to share with you how ceramic flat sheet memory will solve these problems.
Thanks so much, everyone. It was a great pleasure for me and for the Middle East Water Forum to host such event, and with this innovative technology that can be scaled up in our region. And I would like also to thank our panelists for their attention and for being with us. And we will follow up with you on this webinar. We are recording the webinar, and we will share it in our forum and on our social media. And also the presentation will be also at your hand in our forum to be shared. And this would be a good opportunity also for our forum to get to know more about Seraflic and the technology and the applications of it. And we will make sure to share and exchange with different stakeholders in the Middle East Water Forum, and keeping informing people about the state of the art of such technologies that could be applied in our region, which is really needed something like this. I thank you, you all again, and was really a great pleasure, and hope we have now a good number of participants that has been attended to this webinar, and we look forward to next webinars, and look also forward to cooperating with all of you. Thank you so much, and keep safe. Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye, guys.
Bye-bye. Maybe we can take a photo all together. Just one. Yeah, great. Thanks so much. Bye-bye.
Bye.
Thank you. Bye-bye. Bye.
Bye-bye.
Bye, guys.
Bye-bye.
Bye.
Bye-bye.
Julius, telefonieren wir?